All right. I think it's recording. Great. And the course notes is coming from a SIGGRAPH 2012 course notes done by Aptikios Fakis and Yerne Babish. So this is only the first part of the course done by Aptikios Fakis, and he is right now a professor in University of Wisconsin-Madison. I am also doing one of my projects with him, and he's a pretty awesome professor to follow us. All the course notes can be found in this www.famdefo.org, which is a finite element method deformation.org, and you can just Google it and get all the materials that you want on that. By the way, how many of you are choosing like finite element method as your final project? No. Okay. Well. Anyway, let's get started for that. So before I really want to start this class, I want to cover some basics of it. The first thing is a rotation matrix in 3D. We know in 2D, a rotation matrix, in 2D case, a rotation matrix can be always written as something like cosine theta, negative sine theta, sine theta, cosine theta. The negative sign can be here or here. It depends on whether you're rotating it clockwise or counterclockwise. And in here, we know that there are some nice properties about the rotation matrix. Like if R equals to this one, we know that first thing is the rotation matrix is an orthogonal matrix, which means that R transpose multiplied by R is identity. And to be more specific, an orthogonal matrix means that if I write down as the rotation matrix as something like R1 vector, R2 vector, we have something like R1 dot R1 equals to 1 and R1 dot all the x's are not belongs to this one equals to 0. This is the property of the orthogonal matrix. And also it has one more property, is that we know that determinant of the rotation matrix in 2D case is a cosine theta squared plus sine theta squared equals to 1. Because there are also other orthogonal matrices, something like 1, 0, 0, negative 1. We know that this one is not a rotation matrix. You cannot like rotate an object in an arbitrary way and to match this matrix. All right, that's because the determinant of this matrix is negative 1. We know that this matrix is kind of like a reflection matrix. If I have an object here, by multiplying this matrix, it will flip the sign on the y-axis, so it will actually be like an object to this place. Let me draw it in a different shape. So you know that you cannot really rotate it here, but the only thing that you can do is by reflect. Okay, and in 3D, we know those two properties hold too. So in 3D, for an arbitrary rotation matrix, then it's really hard to write it here because it can rotate along an arbitrary axis, not even an axis or line axis. So we know that if a matrix has this property, R transpose R equals to identity, this is an orthogonal matrix, and also determinant of R equals to 1, we know that this one is a rotation matrix, and we are 100% know that we can do our use rotation as our transformation to get this matrix. Okay. The other thing that I want to talk really before the class is the singular value decomposition. So I assume like all of you are familiar with this topic. If I get an arbitrary matrix A, I can do a singular value decomposition to U sigma V transpose, where both U and V are both U and V are orthogonal matrix, and the sigma is a diagonal matrix with all positive elements. So this is the traditional way that we are doing SVD. But today, I'm going to do it in a slightly different way. If A is a 3x3 or 2x2 matrix, because we are simulating everything just in a 3D world or 2D world, we want to also decompose it to something like U sigma V transpose, where both U and the V belongs to SO3, which means that those two matrices are not only orthogonal, but also the determinant of U needs to be 1 and determinant of V needs to be 1. So I add an extra constraint to this decomposition, to this singular value decomposition. And in that case, I am allowing the last element of sigma to be negative. So it's a positive element. The last one can be either positive or negative element. Because it is pretty simple to get from to do the traditional SVD and do some alteration to get our new SVD here. Because if I have a traditional SVD, A equals to U sigma V transpose, and here we know like the determinant of U equals to -1 instead of 1. We can just multiply another matrix. It's 1, 1, 1. Sorry, it's 3D. It's 1, 1, -1 to U, and also multiply this matrix 1, 1, -1 to sigma, and then we can get a U matrix with determinant as +1, but just alter the last element in sigma. And we can do the same thing to V in order to get this matrix. All right. Okay. So when I'm talking about SVD in the following content, I'm always referring to this part. So the sigma can have negative value on the last one, but U and V are both rotation matrices in my 2D or 3D space. Great. So let's start the course. This course is called the Finite Element Method, and it is mainly used. So in this finite element method in like continuum mechanics has been widely used for simulating soft bodies and also some fracture stuff. But here I'm mainly talking about using FEM to simulate soft bodies. Okay, so given a soft body, we want to represent its volumetric elasticity. Okay, so say I have an arbitrary object in 3D. Let me draw something. A bunny. It's a fat bunny, and I'm drawing everything in 2D because it's easier to draw here. But you can imagine this is a 3D object. All right. So the first thing is we want to discretize it into lots of finite elements. Basically, we are discretizing it into really small tetrahedron and tetrahedra. And for each tetrahedra, we want to represent how it is deformed, and we want to get the energy of it, so we can simulate the entire soft body. All right. Okay. So let's get a really naive thing, really naive approach to simulate one tetrahedron. So one tetrahedron have 4 vertices and 6 edges. And if you were told to simulate this one as a soft body, like what is the simplest idea to do it? We can still treat all of those 4 particles just as 4 particles. All right, and we are linking springs between them, like adding springs to all of them. And because we know the spring has its own property, they want to go to the rest pose of every spring. So by using this way, we can kind of simulate the soft body effect. And if I remember correctly, your homework 2 framework has also enables you to add the the ability to import some OBJ file and add springs on it, and then you can not only simulate claws but also simulate some soft body on your mass spring system. Okay, and but what is the problem? Well, if mass spring system is already good enough, why am I like teaching this finite element method? Because mass spring system has some some own disadvantages. So the first one is it's really because all the springs are not aware the existence of this element. All right, if I'm drawn in 2D, I can make a triangle using 3 springs, and if I flip the triangle completely, and all the springs are still in its rest pose. So there's no force basically at all. So if you flip something, you break some tetrahedron, then it will never go back again. All right, so this is the first one. And also, the second one is mass spring system is highly dependent on your tetrahedralization. Or if I draw it in 2D, so if I want to simulate a bar, which has a lot of detail on this end, I can discretize it into lots of triangles to represent the fine detail here. But I don't really care about this part. So this part, I'm going to just make 3 triangles out of it. And because the length of the springs is so different, then it's really hard to determine the stiffness parameter for all the springs over here. And also the quality of the mesh is greatly dependent on how you triangularize this mesh. Okay, so this is why we want to introduce a finite element method FEM from continuous mechanics. Continuum mechanics. I cannot spell without Google. So did anyone of you come from like material science or you? Okay, so you must be very familiar with that.
Pretty much.
Okay, pretty much. Great. So this is the concept we imported from the continuum mechanics, and so the basic idea is to discretize the entire mesh into small triangles or small tetrahedron, and use those triangles and tetrahedron as single elements to simulate our entire simulation. So let me also draw my favorite bunny example. So this is a 2D mesh. Omega belongs to R2, or actually it's a 3D mesh if you can imagine it. It is this is a bunny head like on a 3D space. And what we want to do is first thing we want to measure the how the bunny is deformed from this rest shape omega. We want to measure the deformation. And once we have the deformation, we want to have a string measurement. To tell how much deformation my current deformation is deviated from my rest pose. All right, and once I have the string measurement, it is pretty straightforward for me to get the energy from the string measurement. So basically, I can say if the string measurement is E, and it is like the grain string tensor, then I can simply have the energy like 1/2 of K E Frobenius norm squared, where Frobenius norm means if I have a matrix A is equals to A11 to ANN, then the Frobenius norm is basically like the second norm of a vector. The Frobenius norm of A is the summation of all ij since AI on j squared.
What is K here?
Oh, it's a stiffness parameter. And also it should incorporate some information like the rest post area of the triangle or the rest post volume of the tetrahedron.
Even if it's a perfectly linear material, we still need these two parameters. I mean, we need still need two parameters.
That's true. That's true. I know what you mentioned. We can represent it as a Young's modulo or Poisson and Poisson parameter, or like a Lamé's first and second parameters. But I will talk about later. This is a sort of a naive model. If I have a stream measurement to measure how my current deformation is different from my rest pose, the really straightforward one is to get the energy look like this. It looks pretty much like your mass spring system, all right? Because if we want to measure how much my current spring is different from the rest pose, I'm just measure the current length of the spring minus the rest length of the spring, and then we just basically take the square of it, and this is our energy. Okay, so let's think about it. Let's think about it one by one. The first thing is how to represent the deformation of an arbitrary function. If I have a function phi, let me copy this one. Deformation. This is my rest-shaped bunny in omega. All right, and we know that omega belongs to an R3 space. If I have a function phi, which is a map from R3 to R3, basically saying that I can put an arbitrary point here and move it along this function phi, map it to something else, like a hugely deformed bunny. Right? It is a one-to-one map because we have this function phi from R3, not exactly one-to-one. I can also clap something into zero, but it is a function phi that maps from my original rest shape to something else. And sometimes we are not. Let me show you some example of phi. Like phi can be a purely rotation function, or it can be a uniform scaling function, or this one can be a scaling function on an axis. Basically, it can be anything. Also, it can be translation on something. And also, so for an arbitrary point in this object, we probably only want to measure the rotation and the scaling around its neighbors. We are not really care about the translation of the particle because just simply translated it won't have any effect on this material, on an arbitrary material. So let's define the Jacobian of the phi function. If phi is an R3 to R3, phi can be written as something like phi1, phi2, and phi3. Right? So the Jacobian of it will be partial phi1, partial x, partial phi1, partial y, partial phi1, partial z, to partial phi3, partial z. And we define this as my deformation gradient f. So in that case, I can sort of represent an arbitrary transformation function phi of x equals to something like f. F is a 3 by 3 matrix multiplied by x, add some translation vector. Because we know that all the rotation and scaling matrices are linear operator basically, and the entire phi is an affine transformation. And we can get rid of this t by taking the gradient of the phi function, and we can simply get a deformation gradient matrix f. And f is the way that we represent for an arbitrary deformation. Notice that f in 3D space, it has only 9 degrees of freedom because the translation has already been ruled out. So for an arbitrary element, if I have an element something like this, it has 4 vertices. So originally it should have 12 degrees of freedom. But we can see that we can fix a point here, and I only care about the relative position of all the three neighbors. So we can rule out 3 degrees freedom by rule out the entire translation, and only get 9 degrees of freedom of this element. And those 9 degrees of freedom are in this transformation deformation gradient matrix F. Okay. All right. So given this F, that's hopefully it's still recording. Great, great. Given this deformation gradient, oh, sorry. So by the way, okay, let's think about this element we have already discretized. It has 4 vertices. Like this is an x1, x2, x3, and x4. All right. Because we know that an arbitrary function can be written as this way, and so we know that if I deform it into phi x, let me use the lowercase x as a deformed case. It's usually in all the continuum mechanics book, we are using the uppercase x as the rest pose and the lowercase x as the deformed pose. Although this is a terrible notation, but I'm gonna just follow this rule. And this one, so we know that x1 equals to phi x uppercase x1, x2 equals to phi x2, and etc. etc. We can write it down explicitly into f multiplied by x1 plus t, and I'm going to also write down x2 equals to f multiplied by x2 plus t, x3 equals to f multiplied by x3 plus t, and x4 equals to f multiplied by x4 plus t. In the finite element method, we have an assumption that for each element, because it's already small enough, we can assume the deformation gradient for all the 4 vertices are the same, so they are sharing the same f and t. So because this is a really small element, so we can have this kind of assumption, right? So how to compute this f from the information if given the current pose x1, x2, x3, x4, and the rest pose x1, x2, x3, and x4.
Is this form like a strict form, or is it just Taylor's approximation?
Excuse me?
That equation, is it like a strict equation, or is it just Taylor approximation?
It's not a Taylor approximation. You mean this one?
Yeah.
Not exactly, because if we don't, okay. So it really depends on the phi function, right? For the deformation that we are caring about, for like rotation and for scaling, they're just the linear operators. So the first order Taylor expansion is itself.
Okay.
Right? But if you have some really complicated deformation, like the some of the dimensions are coupled together, like the y dimension is also like dependent on your dimension, x-axis deformation, then this one will only be a first order Taylor expansion on that. So we are just thinking, let's just think about those immediate cases, just the sum scaling and the rotation and transformation on this phi map. All right. So okay, so one straightforward thing is we can substitute x4 from both x1, x2, and x3. So we have three equations: x1 minus x4 equals to f x1 minus x4. They are vectors. And x2 minus x4 equals to f x2 minus x4. And x3 minus x4 equals to f multiplied by uppercase x3 minus x4. So the translation basically goes away. Then we can actually write down it as a matrix form. if I have a matrix dm in material space, it equals to x uppercase x1 minus x4, then x2 minus x4, x3 minus x4. And I can also have another matrix dr equals to lowercase the current pose x1 minus x4, x2 minus x4, and x3 minus x4. We can actually write down this equation as something like dr equals to f multiplied by dm. All right, because both of those two matrices are 3×3 matrices, and this becomes a matrix form. And in order to get the current deformation gradient, if I know the rest pose, if I know the current pose, I can just compute f equals to dr multiplied by dm inverse. All right. So there are two things about it. The first thing is invert this matrix is not a horrible idea. It's only a 3×3 matrix, and only for one. Oh, yes.
I'm not sure what's the difference between dm and dr.
Oh, sorry. So this is the uppercase one. That's why I say that the notation is horrible. Dm is the rest pose matrix, and dr is the current pose matrix. All right. So one thing is that if the rest pose of the material doesn't change, if we are simulating the hyperelastic materials, it always will go back to the rest pose. There's no plasticity of the material. The dm will not be changed. So we only need to calculate it for once for all the elements because the rest pose is there. We are not changing it. Calculate it once, and then we can use it forever. And also, one question is this dm matrix always invertible? Will it be a singular matrix that we cannot invert it?
Yes, if all 4 points lie in the same plane.
That's true. That's true. If so, think about this case. If I put this x4 into the same plane on x1, x2, and x3, then those three vectors are in the same plane. All right. So in that case, the dm will be a singular matrix. So if dm is singular, it simply means your triangulation or your tetrahedralization is terrible. Probably you need to redo it using some other techniques to make sure that all the elements, all the rest shape of the elements are nice enough for your future simulation. All right. Okay. And also another property here is that because we can write down an element using this dm or dr matrix, and what is the volume of the element in the rest pose? Given this dm matrix, it should be pretty straightforward to calculate the volume of it.
Determinant of dm.
Right, that's true. The volume of this element in the rest pose will simply be 1/6 of determinant of dm. And also here I'm gonna put an abstract operator on that because the dm can simply be negative if I put x4 on the other side. All right, and also we know that the current value, the current volume of this element will be just 1/6 of the determinant of dr matrix. All right. Okay. So in this way, we are pretty confident to represent all the elements like in this bunny, and we can calculate the deformation gradient on that. And then we want to see that how the deformation gradient is different from the rest pose. We want to measure the strain of an arbitrary element. So strain and energy. All right. So the most straightforward one, if you want to take an analogy of a mass spring system, so how about we measure the strain as a deformation gradient in itself? And then the energy will be simply like something like 1/2 multiplied by a constant stiffness multiplied by the Frobenius norm of my deformation gradient squared. So I just made it up by myself, but it is clearly wrong, because when does this energy goes to 0 or goes to the smallest value?
When f is 0.
Right, when f is 0, when all elements in this F matrix is 0. All right, it means that that deformation gradient wants to collapse the entire element into the point. And in that way, this one will be a smallest value. It will reach its smallest value. This equation is kind of nice because it's a perfect quadratic function on F. It's really easy to calculate, but it just wants to collapse everything into 0. It's not completely useless because in some of the cases, like image warping or some 2D image synthesis, if I fix the boundary of the entire image as a hard constraint, so all the vertices on the boundaries are not allowed to move, and then it is allowed to collapse everything inside, every element inside into the point, because the boundary will fight against it. So because of the simplicity of this formulation, some of the people are still use it in this image simulation part, or in some 2D simulation part with those hard boundary conditions. You can imagine that even if all the elements want to shrink into a point, the boundary that is against it. And you can see after the simulation, the energy kind of balanced out throughout the entire image. All right. Okay, so let's take a look of the deformation gradient again. Where is my, okay, this is my deformation gradient. So when my entire bunny is undeformed, what is the value of my deformation gradient at that point? Yes, it's identity. Because in that case, dr will simply become the same with dm. So it's a dm inverse, it becomes identity. So one really naive guess of how to measure the strain is to say that I want to use f minus identity as the measurement of the strain. So that the further it deviates from identity, then the larger energy, something like 1/2 of k f minus identity Frobenius norm squared. So the larger energy it will become if I deviate from the identity more. Right. So this one is called a linear elasticity. It's completely linear because it's just the f minus identity Frobenius norm squared. It also has some problem. Because naively we are thinking, okay, the more it's being apart from identity, then the more penalty that I should give on this energy. But think about f. F has 9 degrees of freedom, where 3 degrees of freedom inside is rotation. All right. And we are not expecting any elastic energy under some rotational deformation. If I just purely rotate my object from one pose to another pose, there should not be any force inside it. But what about this one? This one, if f equals to a rotation matrix R, then my energy density psi f will simply become 1/2 of k rotation minus identity Frobenius norm squared. And we know that this one is not zero. All right, it means it acts some non-zero energy on a purely rotational deformation. It is not ideal, and there's a lot of paper in early 2000 to discuss this problem. Try to remove this rotation matrix from from the energy. So the first one is called small string tensor. Sure. So what does this tensor do? This tensor simply, I can write it as epsilon equals to 1/2 of F plus F transpose minus identity. It's not very far away from the F minus identity. It's still a linear form. All right. So in that case, if I have really small rotation, let me illustrate it in 2D. In 2D, the rotation can be represented as cosine theta, negative sine theta, cosine theta. If my rotation is really small, then cosine theta almost equals to 1. All right, so this matrix can almost be thinking at something like 1, negative something epsilon, positive epsilon, and 1. So if I add the transpose of this matrix, it also becomes and divided by 2, and it also becomes an identity matrix. So under really small rotations, and this measurement should be fine if I have the energy something like 1/2 of k epsilon for Benio's norm squared. It should be okay under really small rotation. But what about it's a large rotation? If it's a large rotation, cosine theta is nowhere near 1. All right, so this one will also have effect on the energy. If you have larger and the larger energy, it will also penalize from that. Okay, and then we also have green string tensor. So green string tensor E equals to 1/2 of F transpose F minus identity. So F transpose F is kind of a nice thing, because we can, if you think F as a polar decomposition, F equals to R multiplied by S, where R is the rotation matrix and S is a symmetric part. It's a symmetric matrix. All right, and then by multiplying F transpose F will simply equals to S transpose R S, and the R transpose R goes away, because R is also an orthogonal matrix. It's a rotation matrix, so it becomes S transpose S, and we know that S is a symmetric matrix. It's S squared. So this one get rid of the rotation matrix very nicely. And we can also represent the energy like something like 1/2 of k multiplied by green string tensor for Benio's norm squared. So given an arbitrary rotation, it has no effect on this energy, because in the string measurement, the string tensor cleverly just avoids the rotation by using this F transpose F. All right. So what is the possible problem on this energy? It also has some problems. The first problem is that it is too much invariant. It's not only rotational invariant, but also reflection invariant. Think about F equals to something like 1, 1, negative 1. It is nothing but a reflection matrix that will reflect on the z-axis. It's not a rotation matrix. It should be penalized. All right, we are not allowing all the materials to go just inside out. So, but in this under this measurement, what is the string tensor on that? If F equals to this one, E is 1/2 of F transpose F minus identity. It simply becomes a zero matrix. So this means if I'm using this grain strain tensor as my strain measurement, then I'm allowing the materials to go inside out, to go invert, to be reflected. Okay, and also the second one. The second one is the strain tensor itself is already a second order degree over F. It's F transpose F. So the energy will be a fourth degree function polynomial over this deformation gradient F. All right. So we know for an arbitrary fourth order function, if there's a fourth degree function, fourth degree polynomial, it will be something looks like this. It will have 2 local minimum, 1 local maximum, something like this, or 2 local maximum, 1 local minimum, depends on the sign. All right. This one also happens in our case because it is completely zero when F equals to identity, and this is one of our smallest energy. But also there's another local minimum here when F is approaching to 0. So if you compress the material too much over this one, the material will tend to go to another local minimum instead of this global minimum. So the material, if under a really large compression, the material will go to a point, will collapse into the point. All right, so there are 2 very bad things about the grain strain tensor. But in general, if you're just if you not compress the material too much, you're just expand it a lot, this material works really well. And because it's also a fourth order polynomial over F, and you can also apply your favorite model reduction technique on that. So it can be simulated in a very fast way. Yarnay Barbiche has lots of paper on that, to just simulate a very complicated model in real time. So, okay, grain strain tensor. So remember that the idea of grain strain tensor is to use F transpose F to cancel this rotation R out. So what if we can directly cancel the rotation R out by using some of the technique, like something I mentioned at the beginning of the class? There was a Stanford paper to directly calculate the singular value decomposition out of an F. Let me see this co-rotated linear elasticity. Elasticity. Okay, given a deformation gradient F, I can compute the SVD out of it. I can compute U sigma V transpose. Whereas I said both U and V are rotation matrices, and sigma is a diagonal matrix. Let's think about this sigma. Sigma equal to sigma 1, sigma 2, and sigma 3. And those 3 values can be seen as a scaling parameter after a change base operation. Right? So if I'm using this sigma minus identity as my strain measurement, I can simply represent the energy as something like 1/2 multiplied by K multiplied by sigma minus identity Frobenius norm squared. I can use this one as my energy. And this one looks reasonable because because it already cancels rotation out and only leaves a scaling parameter after the change base operation. Or because this is a Frobenius norm squared, I can also write it down as 1/2 of K. Like, I'm going to multiply the rotation matrix back because if I multiply an orthogonal matrix in this Frobenius norm operator, it has no effect on the Frobenius norm minus I multiplied by V transpose for Frobenius norm squared. All right, and this one becomes 1/2 of K deformation gradient F minus R for Frobenius norm squared. And this R is the best fit rotation UV transpose of my current deformation gradient F. Okay, so this one sounds reasonable, really reasonable, because it cancels rotation nicely. It is also a linear elasticity model. It's a second order polynomial on F. And but think about it again. Think about it again. How many degrees of freedom are there in my strain measurement right now? 3. Okay. So originally I'm 9. All right. So we won't rule out of the rotation, which is 3 degrees of freedom. But where is the other 3 degrees of freedom gone? Because so think about this F. Now by measuring using this sigma, I can have the energy density phi F equals to phi R multiplied by F. All right. Because if I multiply F by R, it will only multiply by this U matrix by another R. This one is still in rotation matrix. It's fine. It's completely fine. After the singular value decomposition, the sigma is the same. So this one we call this material rotational. It's rotational invariant. It's good. This one is the property that we want. But if we are measuring the string like this way, I actually have another property by accident. It also equals to F multiplied by R on the right hand side. Think about it. Think about it. If I multiply by an R matrix on the right hand side, it will only multiply by something R transpose on the V matrix. And it still hold the VR transpose matrix is still a rotation matrix. My sigma is not is also not changed. Right? It means that, what does it mean? It means if I have a ball, if I compress it over here, or if I rotate it and still compress it on the same direction, I got the same response. And this is what? This is isotropy. It means that the material has the same response for all direction compression or elongation. All right. For lots of materials, it's not a problem. If you want to just simulate a Jello cube, it should be an isotropical material. You drop it on this side, or you drop it on another side, you should get the same response. So in that case, the co-rotated linear elasticity should work perfectly fine. But if you have other materials, like if you have a concrete, which has a steels inside, all right, it should has really, like, it should have different material properties on this direction and on this direction. In that case, if you still want to use your co-rotated linear elasticity to simulate it, it's probably not a very good idea, because you only have 3 degrees of freedom to represent your deformation gradient when you are measuring your energy. Other than that, it is really good. Also, there's another bad, not so bad thing about it. It's just because when you're simulated for every frame, you need to do singular value decomposition for all the elements. It can be done in parallel because all of them are independent. Just to use your GPU to do the SVD separately. It should not be a very big problem, but if you're running a simulation on CPU, it will probably take you some time to do it. Because and even in 3x3 matrix, SVD will also take you some time. Okay. All right. So let's fill this form. So in this class, at first we have a really naive model that I take, which is like an analogy of a mass spring system of springs. It's F minus identity, and the energy is simply 1/2 of K, something like F minus identity for Frobenius norm squared. And we know it has some bad properties, all right? It's not a rotational invariant. And we have a little bit better model. It's also linear elasticity. It's based on small string tensor. Which is the string measurement is basically 1/2 of F plus F transpose minus I. And we can measure the energy as something like, I'm going to write down here, mu multiplied by Frobenius norm of epsilon squared. It also has a problem because it's not solving the rotational invariant problem completely. It only has a nicer property when the rotation is small. But if the rotation goes large, it will also be bad. All right, it's not completely rotational invariant. We have another string measurement using E equals to 1/2 of F transpose F minus I. This is a grain string tensor. And this model is called the St. Venant-Kirchhoff model. I'm going to also put the energy density as something like mu multiplied by E Frobenius norm squared. We know there are several bad things about this model. This one is reflection invariant, which is not very good. And also, this one is a fourth order polynomial. So it has multiple local minimums. When you're running optimization on this energy, it might get you to a bad state. When you compress the material too much, it will collapse into the point. Okay, we have a co-rotated linear elasticity. In this model, we are simply measure the strain as an epsilon minus identity, where epsilon comes from the singular value decomposition. And then we are going to measure the energy as something like Frobenius norm squared. All right. The only bad thing is I need to do polar decomposition on that, or SVD on that, which is kind of slow, not very slow, but slower than the previous method. And also it can only represent for those isotropical method, isotropic materials. Also, for most of the materials, it is nice because you can think of them as isotropical materials. So before I introduce the last model that I'm going to talk in this class, I'm going to say something a little bit different about the energy density. Because as Valentin said, there should be at least two parameters to represent a soft model. One is Young's module. It's like the parameter that we are writing it down here to represent how the material is going to push against my compression or my elongation. All right. So it has the property that it wants to go to the rest position. And also another one is, think about it. Think about this one. If I have a model under two kinds of deformation gradient. The first one is to pull it out to a bigger square. So the deformation gradient is something like 2, 2. All right, and also another deformation gradient is something like pull it out in one direction and compress in another direction. And the deformation gradient f here equals to 2, 1/2. Not 2. Let me not put it that hard. To 2/3. Sorry, to 1.5. All right. So if I substitute any kind of my energy, not this one. If I substitute any kind of my energy density here, like my favorite co-rotated linear elasticity, and what is the epsilon of those deformation gradient? It's themselves, right? Because they are already diagonal matrices, and then my energy will be something like mu multiplied by f minus identity for Frobenius norm squared. Here I write down f. Actually, it's an epsilon, but they're the same. It's mu multiplied by 0.5 squared plus 0.5. It's mu multiplied by 0.5. And here, it's the same thing. It also equals to mu multiplied by 0.5. It means that it has really no difference on those two deformations. Even if I really want to stretch it out in a hard way, or this way looks more naturally, because if I squeeze it on one direction, it got to expand on the other direction. Because this one has it's preserving its own volume or its own area. Right. So ideally, I should have another area preservation term, or in 3D volume preservation term, which is correspondingly we use a Poisson ratio to represent that. For example, if I have a material like a square and I'm pull it on two ends of the square should look like something like this. Right, because once it's pulled on those two directions, and in order to preserve the volume, it should be compressed in this direction. It behaves more naturally. Okay, there are some materials with a negative Poisson ratio, so if you pull it on this direction, it expand on the other two directions. People just print it in some 3D printers, but it's really rare to see in the real world. So ideally, we want the entire volume of the object to maintain the same. So we know that for one element, something like this. What is the current volume of this element? It's 1/6 of the determinant of dr squared. All right. Or we know that because dr equals to Frobenius, deformation gradient multiplied by dm inverse, and so we know that the volume of it equals to 1/6 multiplied by dr equals to deformation gradient f multiplied by dm, so it's determinant of f multiplied by dm, which is 1/6 of determinant of f multiplied by determinant of dm. I'm pulling this 1/6 to this side. This is my original volume, and the determinant of f is the change of the volume. Okay, so this one is kind of interesting. If I really want to get the volume to be something constant, I can simply add a term, something like determinant of f minus 1 squared. And if I can add this term to the energy, I'm adding a soft constraint on that, and it wants to preserve the volume as much as possible. It wants the determinant f equals to 1. I'm not putting it as a hard constraint because sometimes materials do lose some volumes, even if it's really a hard material like a desk. Under a really large compression, it will also lose some volumes, but a little bit. So here I'm only put a soft constraint onto that. Okay, so if we pull out our favorite linear correlated linear elasticity model, it becomes determinant of U sigma V transpose minus 1 squared. And we want this one to be as close to 0 as possible. And we know that also because it's a determinant, we can separate out. It's a determinant of U multiplied by determinant of sigma multiplied by determinant of V transpose minus 1 squared. Both U and V are rotation matrices, so the determinant of them equals to 1. And it only leaves the determinant of sigma. We know that sigma is a diagonal matrix. Sigma 1, sigma 2, sigma 3. So that it becomes sigma 1 multiplied by sigma 2 multiplied by sigma 3 minus 1 squared. Okay, it seems easier. And again, it's also not that good because sigma 1, sigma 2, sigma 3, this is already a third order polynomial, and if I span it out, it will be a 6th order polynomial over all the sigmas. So here, I can approximate it. You need to trust me. I'm omitting lots of steps. Sigma 1 minus 1 squared plus sigma 2. Sorry, it's something like sigma 1 plus sigma 2 plus sigma 3 minus 3 squared plus some higher order terms. So I'm only have the second order terms over here and omit all the higher order terms. And what is this one? Sigma 1 plus sigma 2 plus sigma 3, this is the trace of the sigma matrix. And the 3 is the trace of an identity matrix, because if you sum up all the identities, it equals to 3. All right. So this one can also be written down as the trace of sigma minus identity squared plus some higher order term. This one's better. It's again a linear term. It also kind of preserves the volume if the volume changes not so much, because you can see this one can be seen as a linearization at sigma 1, sigma 2, sigma 3 equals to 1. It's just I'm just omitting the higher order term, expanding it using the first order Taylor expansion, and this is how it is. All right. So think about this one. I can add it back to my favorite correlated linear elasticity. It's adding 1/2 lambda multiplied by the trace of sigma minus identity squared. And you can see this lambda is so here lambda and mu is Lamé's first and second coefficient. Or you can think of this lambda is more like the efficient, like your Poisson ratio, and this mu is more like the coefficient, like Young's module. So this one is against all the deformation, but this one allows it to deform but only preserve the volume. All right, and I can do the same trick to all the model above. I can do 1/2 of lambda, this is the trace square grain string tensor squared, or 1/2 of lambda trace small string tensor squared, and they all have those kind of properties, and they preserve the volume preservation property well. Okay. Okay. So last one. There is a last one that I'm missing here. It's called the Neo-Hookean model. So because we want to, this is also a higher order model. It's a little bit more complicated, but we have all the information that we want. So Hookean model. So in order to get a rotational invariant term, we have something that is proper to do, like F transpose F. This one is rotational invariant. Although it's also reflection invariant, let's just put it here. All right. And also, where Neo-Hookean model is measuring the string as something like this, I1 equals to determinant of F transpose F. And when F equals to identity, this one equals to 3. So I1 minus 3 is something that it wants to preserve. And also, like I3 equals to determinant of F squared, or J equals to determinant of F. This is a volume term of it. So the Neo-Hookean model simply puts the energy like 1/2 of mu I1 multiple minus 3 minus mu log J plus 1/2 of lambda log. This is definitely more complicated, but think about it one by one. I1 minus 3 means that I really want the determinant of F transpose F to be 3, which is a pushing F towards the identity matrix. Not exactly, but also it wants to minus mu multiplied by log J, and we know that log J is determinant of F. All right, and we know that the thing Van and Kirchhoff model is also reflection invariant because I can put F into the another side. But what if I add a log, negative log of determinant of F here? It means that determinant of F cannot be negative. I can no longer put my reflection matrix like 1, 1, negative 1 here because the negative log function will boost the energy to infinity. This is a negative log function around that row. So you can never reflect it. All right, and also it has another term. It's like 1/2 the lambda multiplied by log squared J. It's more like it is also a term that preserves the to make the material to stay on the positive side of it. All right, so this one also looks nice. It also has some bad properties. So one thing is once one of the elements is nearly to be compressed to a point, or not a point, to compress it to 0 volume, the energy will go to infinity, and it will cause you some numerical problems. And also it looks more complicated. It's also described in this course note. So if you're really interested in this material model, just go to the course note and take a look at this. Okay, so now I have summarized the properties of all the constitutive models. On next class on Wednesday, I'm going to do the discretization and tell you how to simulate the entire finite element method to simulate soft body using finite element method using all those models here. All right. Okay. Thank you. Oh, by the way, let me close it and play some YouTube video.